So this is how you write your code and simulate using Quartus and ModelSim. So the problem here is we are designing the counter. The first step is write the VHDL code for the D flip-flop. You have already done this for the lab. This is the same code. Make sure that it's the top level entity and compile the program. If your compilation is successful, you get this confirmation message. So your flip-flop is successfully compiled. As I've said before, I'm not going to test this circuit. I've already tested this before, so I'm going to leave that to you. Now let's open the main file. So which is the actual design. So counter design. Now this was the counter design that I gave you before in the video. So it had two inputs, clock and reset, one output Q, which is a 3-bit vector. Then we are using this component here. So that's the component part that I included the component. I have a couple of signals here, Q bar and D2 input. Q bar is not of Q2 or not of Q, and D2 is this equation. We have already seen this in the design. And these are my 3 flip-flops. I'm going to invoke them and port map. So let's compile this design. So make sure I set it as the top level entity and compile. But I'm going to get one error here. Okay, there's the error. So the error is in line 19 of counter design, which is basically this one here. So the error says interface object queue of mode out cannot be read. Change object mode to buffer. If you see this here in line 6, Q is declared as an output. In VHDL, if you declare something as an output, you can only use it on the left-hand side. You cannot use it on the right-hand side of the equation. Now here, Q is used on the right-hand side of the equation, which is why it is throwing an error. Now to fix this, I can make Q as a buffer. So a buffer can act as both an input and an output. So save this and recompile. Now it's going to run successfully. So once it is done, you'll get a confirmation message saying that the design has been successfully synthesized. There were no errors and my compilation was successful. So I was able to successfully synthesize my design. So close this. Now the next step is to see what circuit got created. It's not compulsory, but it's just a good idea to see that. So you can see that in RTL viewer. So that should be in netlist viewers, RTL viewer. And this was the circuit that got created. So this circuit is very much similar to the design that we have come up on paper. So Quartus also produces the same result. You can close this. Time to run the RTL simulation. Okay. So open work, counter design, architecture, simulate. So those are my signals, clock, reset, and Q. We don't need to worry about Q bar and D2 input because they are internal signals. So if you open this up, you'll see that you have in, out, and internal signals. So let's take clock, modify, apply wave. I'm going to set it to 2000 picoseconds. Initial value 0 with the clock period 100. Finish. So that's my clock. Next, I'm going to give value to my reset, apply wave. I'm going to use it as a constant, 0 to 2000. Next, value 1. Now I want my initial reset to be 0. So at least for one clock pulse, I'm going to set it as 0. Go to edit, modify. So start time is, let's say, 25. And end time is, let's say, 125. Next, 0, finish. Now you can see that from 25 picoseconds to 125 picoseconds, my reset has gone low. And Q is my output, so I just right click, add wave. Now my reset is 0 at this rising edge of the clock. So that is when I'm going to start my sequence, which is I'm going to start at 010 from there, right there. So change this to 2000 picoseconds and we hit the run button. So when reset is 0 and at the rising edge of the clock, the sequence is reset. So we are starting at 010. At the next rising edge, my reset signal is 1. I set it that way. So I can start counting my sequence. So from 010, if I get another clock pulse, I move to 100. From 100, if I get another clock pulse, I move to 000. From 000, I get my fourth clock pulse, I move to 011. And then for my fifth clock pulse, I move to 010. And the pattern repeats over and over again. So this is what a counter does. Now, at any instance of time, if my reset is moving to 0, I go back to my original sequence. It is not depicted here, so let's try that. So edit, modify wave. I'm also going to set, let's say, from 325 to 425. Next, I'm going to set that as 0. So finish. As you can see, there is another clock pulse where reset is 0. So let's restart the simulation. Okay, so your initial sequence for your first reset, it's gone to 010. You get a clock pulse, 110. You get another clock pulse, you go to 000. Now for the next clock pulse, my reset is 0, so my sequence is reset, which means I go back to 010. Again, reset goes high for the next clock pulse, and the sequence starts counting. So you go from 010 to 110, followed by 000, followed by 011, and then repeats all over again.